Hi again, Year 12. I've decided to make some videos for you guys for the next chapter as well. We're going to try maybe a bit of a flipped classroom format to help us move quicker through the work, but it means different people can be working at different paces as well. So in your OneNote, it is under tab 22, normal distribution. And we're starting with, it's chapter 24 in your textbook, and we're going to start with 24A, which is the normal distribution. So let's just have a look. Let's go through some of the theory together, and we'll do one or two examples. So this whole chapter, we're just building on what we did in the last one, which was in discrete random variables. And we sort of tied binomial theorem into that to be able to find binomial probability. Now we're looking at a bit of a more statistics focus, but still drawing in some probability into here as well. Now, in the last chapter, when we were doing discrete random variables, let me just grab my highlighter. Hang on. Yep. So we were doing discrete random variables before. Now remember discrete means they're like integer numbers. And this was always in the context of binomial probability, where you have, like, say, the event and the non-event, okay? And then we had a random variable capital X or big X, and this is what we said here. They have to take, little x has to take non-negative integer values, 0, 1, 2, 3, 4, all up to n, say, and n is an element of the natural number set. So, an example could be, x could be, say, your discrete random variable could be the result on, like, rolling a die, okay? Could be a result on rolling a die, for example. But what is the sample space? What are the actual possibilities that you could get? Actually, I might just change this instead of an arrow. I'm going to change it to a colon. So it could be, you could have, actually that won't work because there's no 0. Sorry, not 0, but x could be, little x could be, the result could be a 1, 2, 3, 4, 5, or 6, right? They're all the possible results you could get for rolling a die. Okay, now we're looking at continuous random variables, more so. And little x can take any real value. So maybe one of the easiest examples to use is to think of, like, height or weight. The value of x is not an exact integer number. The number is on a scale or a continuum. Okay, so it could be any decimal or fraction of a number between those integers. So that's your continuous random variable. Now we can summarize each sort of scenario with a probability density function, okay? And it defines how the probability is distributed across sort of the different results, and it's a visual way for us to see where the mean is and how much, where sort of like the spread of the data as well. Now this is touching on a concept we learned back in calculus, which is actually really cool. So to actually find the probability, you find it by calculating areas under the probability density function curve for a particular interval. So you can see that here on our little diagram here. If, for example, I wanted to find the probability of getting, say, something between, like, values C to D here, if I find the area under the probability density function there, which I've highlighted in green, that'll actually tell me a numerical value for the probability. Now, with your probability density function, I'm just going to introduce some sort of different notation here, but you're actually already familiar with it. We know that to find the area under the curve, we can integrate, right? So let's say your domain is this. X has to be greater than or equal to A and less than or equal to B. We would say the area, or the integral of the function, okay, between B to A here of your function is equal to 1, because in this case we're actually setting the whole domain of the whole function is between a to b. So probability of everything should end up as 1 at the end. Like it's a total of all the probabilities. It always should be 100%, right? Should add up to 1. But if you wanted to have a look at just a particular small interval, so here, let's say I wanted my, I wanted to know what's the probability of me rolling, say, a 3 to a 5, for example. So it might be 3, 4, 5. We would say the capital P probability of getting a continuous random variable x between c to d is the integral between c to d of your function fx dx. Does that make sense? Okay. I'm just going to highlight this for you a little bit better. Okay. And so we would have to just integrate and do it as normal, or you actually can use a calculator. So you'll actually be using your graphics calculator and this will just calculate it for you. Okay, I'll get back here to go back here and highlight for me that when we're talking about the probability density function, f of x has to be greater than or equal to 0 on its entire domain. So that means it's above the x-axis, right? So you can see in our diagram here, it's above the x-axis. F of x is greater than or equal to 0. Okay, now if your continuous variable x, has a probability where big X is exactly equal to a particular value is 0, that just means we would write it out like this. P bracket big X is equal to little x is equal to 0 for any little x. Okay. All right, let's have a look at this example here just to sort of build on the idea a little bit about this notation. Let's say we've got an egg, okay, and what's the probability of an egg weighing exactly 72.9 grams? It is actually 0, okay, which is what we're saying up here, okay. And you might think, well, that's a bit weird. Shouldn't there be still a possibility of an egg weighing that much? And the issue is, it depends what you're using to measure it. If you weigh an egg on like the scales, you might just be to the nearest 0.1 grams or 0.01 grams, for example, whatever. You could actually be, your egg could actually be 72.85 grams. That would still round off to 72.9. Or the egg could actually be 72.95, well, up to that much, but not equaling that much. So it could be between 72.85 grams and 72.95 grams, right? As it will round it up to 72.9. So, and you could just keep going. You could just keep adding more decimal places that are going to round up or round down to that amount. So no matter how accurate your scales are, you're ever only going to know the weight of the egg within a range. It's always going to be a range. Let me just circle that better for you. Okay, it's never going to be exact. So for it to equal a particular value, okay, it is going to be, the probability is 0. So for continuous variables, we only talk about, okay, highlight this bit for me, only talk about the probability that an event lies in an interval, okay, not an exact value, whereas all the ones we did in the last chapter were exact values. Well, sorry, not exact, integer values. Okay, that's a better word. Okay, so technically, these are all true here. The probability of continuous variable x being greater than or equal to c, less than or equal to d, is the same as this, and this, and this. We just changed the inequality signs there. All of them are actually equal to each other, okay, between c and d, even if it equals or doesn't equal to the boundary value of c and d, because we're looking at an interval anyway, okay. If your variable was discrete, it would not be true, okay. If your if your random variable is a discrete integer whole number, then that is not true. Okay, because we're talking about an interval, the area under each of those curves between C and D, even if it equals to the value on C or D or not, they're still going to equal to each other. Okay, so yeah, a bit of a tricky concept to get your head around, but yeah, take your time, let it sink in. So the probability distribution that we look at the most, which actually occurs probably the most in real life, is the normal distribution. And you've definitely seen this word before probably, or at least this graph, which the nickname is like the bell curve. Okay, so that's your most important distribution for a continuous random variable. And yes, lots of things in real life take on this sort of behavior. So you might, for example, say, looking at the scores of tests taken by a large population, could be like the crop yields of a farm, excuse me, or it might be, for example, you do a survey of people's heights, weights, and arm lengths, or something like that. And usually the data will take this sort of shape, which is really interesting. And the easiest one to think of, is probably like the test one. So you can imagine if you, say, did a test in class, and then you put out the results, and if this is the mean in the middle, most people get around the average or the mean, right? And then less and less people get a high mark, and very few people get a super high mark, right? And then after the below the mean as well, less and less people get a smaller score, and then over here, very few people, for example, get a super poor mark, or like 0, for example. Okay, so I think that one is the easiest one for us to get a bit of a physical grasp on the idea, because we're used to, taking tests and results and recording results and that kind of idea. Okay, let's have a look at the normal probability density function. So this is it here. This is the equation for the probability density function, which gives you this bell curve shape. Okay, so this is how we write it, right? Your variable x is distributed as normally distributed, where mu is your mean and sigma squared is the variance of your distribution. So just don't forget, this symbol means like is distributed as. Oops. Okay. N is, I guess, for normally distributed, whereas before we were using B for binomial distribution back in the last chapter, a capital B. And yes, mu is mean and sigma squared is your variance. Now, this equation here is pretty full on. We're going to explore it a little bit more. And this is true for x between minus infinity and infinity. Let me have a quick look. Let's have a quick look at our formula booklet, actually, to see where, if this is in our formula booklet. It might not be. This one here is going to come, we're going to come across later, this one, in this chapter. But I think it looks like that one is not in your book, your booklet. So you might have to remember that one, actually. There we go. Okay, so we might need to remember this one, I think. The normal distribution, the probability density function for normal distribution. Okay, so if you have, for example, a curve like the one in this picture below, we would call it a normal curve, or like a bell curve, but normal is the proper terminology. You can see it's symmetrical. You can see symmetrical about the line x equals mu. Okay, you can see here's your mean or your average. Now as x gets closer and closer to infinity towards the positive end and the negative end, you can see your curve is approaching an asymptote. It is approaching the x-axis, right? Yeah, so make sure you have arrows on the ends as well to show that it keeps going. Okay, and just show as accurately as possible in your diagram, if you have to draw it, that it's approaching 0. Now the function is above the x-axis, so f of x is greater than 0 for all x. Yes, we knew that. Okay, that was part of the definition earlier. And the total probability, so the total area under the curve, should always all add up to 1, because it includes everything. Okay, I'll just highlight that for you. That's when we about it though between minus infinity to infinity, because it's covering everything. Okay, so you can see here, oh yes, there's just a note here to remind you that, yeah, the bulk of your scores are around the mean or the middle. Okay, sorry, not the middle, the mean or the average. Okay, now we're going to do a little bit of calculus here, a little bit of theory. Probably not likely to ask you to explain this, but it will deepen your understanding anyway, and hopefully it will still be helpful. So this is just looking at here, it's titled the geometric significance of mu and sigma in your textbook, but I guess it just means how do we see or represent or visualize mu and sigma on the graph, like physically. Okay, now if I take the equation of the function, the probability density function, and if I differentiate it, okay, so you can see here that it's actually just like this big number in front and then e to the power of that, whoops, that monstrosity up there. So really it's just something like, you know, y equals a e to the, you know, bx. Okay, now remind me, how do I differentiate this? Remember, you differentiate the power on top, so derivative of bx is just b. So I'm going to put the a still there, pull the b down, okay, and then it's still e to the bx, right? Okay, so that's what we need to do here. So with f dash, we've got to differentiate this up top and then bring it down the front. So if you differentiate that, when you have a look at it, let's see, we would bring the 2 down. So minus a half times 2 will be -1. So I think that's why we have this negative here. Okay, just rub that out. And then you still have sigma root 2 pi on the bottom, because that's just the number in front. So that's still there. It's kind of like how this a over here is still there afterwards, right? We just leave it there up the front. The only difference here is there's another sigma, which becomes sigma squared. Okay. Now, where that has come from is in this power up here, right? How do we differentiate this? Yes, bring the power down, take 1 from the power, but you've got to times by derivative of the inside. And can you see you've actually got in here, it is actually x over sigma minus mu over sigma. Sorry, I didn't draw that very well. And then they put it all over the 1 sigma, and it's squared. So if you think about it, if you still multiply the derivative of the inside, this is a 1 on sigma in front of x. Okay, so when you differentiate, the x will become a 1. So you just get 1 over sigma. So that's why we have an extra sigma in there, over there. Okay, so that's f dash. Now f dash, or gradient function, right, is going to be 0 at the very top here, right? Because this is where the gradient is flat, isn't it? So f dash is equal to 0 there. It is 0 slope. And we know that is at the point of the maximum point, but that's also where your mean is. Okay, does that make sense? So that will help us find the mean. So if we differentiate again, same idea over here. I might not go through all the maths with you, but same idea. You've just got to differentiate the top again, so I might change color. So over here you've got to go differentiate this again, bring it down, take away 1 from the power, and then I think they just collected out a common term over here just to make it a little bit nicer, and so we should get all of this. Okay, let me rub this out so it's a bit clearer to see. Okay, good. Now we know that f double dash there will also equal to, well, actually we just know we want this to, let me have a think, hang on. F double dash x equals 0, if we let that equal 0, because it could be a point of inflection, right? Okay, that's right. So that's a bit of revision. We need to put that in here. So that's a point of inflection. If f dash equals 0 as well, then it could be a horizontal point of inflection. And then we also need to show that concavity changes either side. Here they don't do it, but if you have to prove the nature, then that's what you would have to do. So here we've got the f double dash is equal to 0. And you can see if it equals to 0, because if you have all of this equals 0, and this is a times in between, you could equate this equals 0, then you could also do this equals 0. But the exponential, that bit will never equal 0, right? Your exponential curve approaches 0 but doesn't. So this half over here like gives you no solution. Does that make sense? But then you can still get a solution here. Yeah, we can do that. We're allowed to do that. So that's what they've done. Okay, over here. So if I let this one equal 0, let me change colors. Yeah, this one here. If I let this one equal 0, right, you can see you could bring one value to the other side and then we get left with this. Okay, might be nice to move the negative one over, so then you get all positives here. And then we're just going to divide, probably multiply both sides by sigma, or multiply the sigma cubed over and then simplify, so we get x minus mu all squared equals sigma squared. Square root both sides, okay, add mu to both sides, and now we have a really nice expression for x. X is equal to mu, which is your mean, plus or minus sigma, your standard deviation. So that means the points of inflection are at mu plus sigma and mu minus sigma, and you can see that here. Here's mu plus sigma and mu minus sigma. So those points of inflection there are one sort of lot of sigma away from the mean, and that is actually called the standard deviation. Okay, so that size of sigma is your standard deviation, right? So let's have a look. So let's highlight some information. So for a normal curve, normal distribution, your standard deviation is uniquely determined as the horizontal distance from the line of symmetry x equals mu to a point of inflection. Okay, so that's like a geometric explanation of it. Now this looks a little bit complicated, but you'll get more used to just using it over time. And it is also something that you have to remember and memorize. It is not going to be in your formula sheet, I'm quite sure. So here's your normal distribution here. These percentages are actually always the same. It's always the same sort of spread and proportions in terms of like the percentages of scores in each standard deviation. And so here's the breakdown here. If you're one standard deviation, so one sigma above the average or one below, here mu minus sigma, okay, here all the people that occur in here is about 34.13% of, say, the whole population that you've surveyed or whatever. And remember, it's symmetrical, so this side is the same. Okay, so altogether it is like 68.26% roughly. And it's going to lie between x minus mu and x sorry, not x, mu minus sigma and mu plus sigma. And then the next portion along is about 13.59% on the left and the right. But when we add it together with the yellow as well, the pink and the yellow, that covers like 95%, 95.44 to be exact, of all the scores, all the data. So let's say it's about maybe, year 12 students doing a maths test. Okay, you'd be able to probably model it quite well with a normal distribution like this, where, about 68.26% of the kids will get one standard deviation away from the mean, and then 95.44% will get it between x minus 2 sigma and mu plus 2 sigma. And then if you go to plus 3 sigma, okay, and minus 3 sigma, it is actually 99.74% of your value, so most of them. It is only sort of after this point here and here does it get super small, and because it is an asymptote as well, we sort of say it approaches 0, and then it's like roughly, it gets close to 100 or keeps approaching 100% basically. Okay. Okay, let's have a go at an example. So here it says the chest measurements of 18-year-old male footballers are normally distributed with a mean of 95 centimeters and a standard deviation of 8 centimeters. Okay, so let's highlight some important information. The mean is 95 centimeters, standard deviation of 8 centimeters. Okay, question A says, find the percentage of footballers with chest measurements between 87 centimeters and 103 centimeters. Okay, first let's visualize what we're doing. So if this is like your distribution, normal distribution graph, okay, it says it's normally distributed, so that's why I know it has this shape. And let's say, I'm gonna draw this a little bit closer. Gee, that's not very good. Let me draw it again. Okay, there we go, a bit closer. Looks like it's approaching x-axis. This is your mean here, which we put as mu, and our mean is 95 centimeters. Good. Now it says standard deviation is 8 centimeters, so that's sigma, right? Sigma is 8 centimeters. So that means 1 sigma more or less than mu. Okay, that means this is an 8 centimeter increase or an 8 centimeter decrease, and this is like mu plus 1 sigma. Yeah, this is mu minus sigma. Okay, does that make sense? So what are those values actually? I'm just going to make this bigger so we can see better. Okay, well, 95 plus 8 means we'll get 103 here, and then 95 minus 8 is going to be 87, right? Centimeters. Okay, and that works out well because for question 1, it's asked us what percentage of footballers with chest measurements between 87 and 103. So you can see it is that first chunk around the mean, which was about 60, like around about 68%. Okay, or if we want to be exact, what was it? 68.26. Okay, so we could say here about, approximately 68.26% of footballers have a chest measurement between 87 to 103 centimeters. Okay, all right, so that's that one. Part 2 asks us to look for 103 to 111 centimeters. Now we've got 103 there. Now if we get 111, let's see, if we add another 8, that'll work, won't it? If I add another 8 centimeters, that'll get us to 111 centimeters, which works out well. So that actually means it is 2 standard deviations or 2 sigma away from the mean. So it's like mu plus 2 sigma. Does that make sense? So this value is mu plus 2 sigma. Okay, but what was that extra portion? It was 13.59%. Okay, but we want to know, yes, between 103 and 111. So that will be, won't it? 13.59%. So around about 13.59%. Okay. Which is just, actually I might change the color so you don't get confused. I think let's make it pink. That's better. Okay, so that's that portion, which is the 13.59%, because I want it not from the mean, but just between 103 to 111 centimeters. Okay, so approximately 13.59%. You can make it a full sentence, so I'm just going to leave it. And then part B says find the probability that the chest measurement of a randomly chosen footballer is between 87 and 111. Now you can see that's all of our yellow and pink highlighted bits, isn't it? From 87 all the way to 111. So we can just add those percentages together. So what were they? So total percentage is like 68.26%. That's the yellow plus the pink, which is 13.59%, which is I should put, because it's all of it is really an approximation, I probably should put approximately, because we've rounded off really. If we do this on the calculator, we get, I've written it down, 81.9%. Okay, so probability though, percentage is okay, but normally probability we give a decimal or a fraction. So we should say therefore the probability is approximately 81 point, no, not 81 point, sorry, I'm going to change the decimal. It's approximately 0.819. Okay, 3 sig fig. All good. And then question C says find the value of K such that approximately 16% of chest measurements are below K centimeters. Now let's have a think. If it is below the value of K, so that means that's the K is, you know, one of these values along here, okay, that I'm planning ingredient at the moment. So I want to know what value of K will it be, like down here or up here, so that K will represent 16% of the chest measurements. Now 16% was around, let's have a think. Well, if you have, this is about what, 34, and then you've got 14. Now if I do, let's have a look back up here, hang on. Now if you have the yellow parts, if that's 68 or 34%, okay, I think this is what we have to do. If this is X, Okay, that's your mean is mu. Now this portion in here, I'm just going to round off. I'm going to say it's roughly 34% and 34. And then the next bit, the next standard deviation over, was about 14%, roughly. So there we've got 48 in 1/2. So down here, it's approximately 2% if you keep going to make, because it's 50-50 on either side, okay? But you could keep going and break it down into something smaller, but I'm just going to leave it there. But this is where I thought we could get the 16% from in the question, because here 2% plus 14% approximately is 16%. So you can see there, okay, the value of k is going to have to be this value here. Okay, so k then is going to be mu minus one of the sigmas, which is actually one that we have already done. It is, what, 95? Take away 8, so we get 87 centimeters. So k actually has to be 87 centimeters. Okay, that was a long one, quite chunky. I mean, it's all new work, so we've got to take time to understand, but you need to do lots of questions, and if you do, more, you will get more familiar with the values inside the normal distribution. Okay, so please practice. We're doing, this is exercise 24A, and it is on page 634 in your textbook. There we go, and have a go, mark your work, and let me know if you have problems.